Yeah, okay. Good morning, everyone. I am Archit, and today I'll be talking about quantum superdense coding. So I'm just gonna quickly do a quick revision of like the basics that we've done many times already. So we know that we can model a qubit not as just either a pure 0 or 1 value, but a superposition of 0 and 1 values. And this is denoted mathematically using a state vector, which we call psi, ket psi, which is a linear combination, otherwise known as a superposition of the 0 and the 1 basis vectors. And alpha and beta, which are their coefficients, refer to their probability amplitudes. And we can naturally see that the probability of measuring 0 is the square of the magnitude of this alpha coefficient, and the probability for measuring 1 is the square of of the magnitude of this coefficient beta. And obviously, the sum of these probabilities of measuring 0, that is the square of the magnitude of alpha, and the probability of measuring 1 must satisfy a normalization condition of 1. Because the qubit, whenever it's measured, must only collapse to a state of 0 or 1. And we've also seen the different ways of representing these state vectors using vectors directly as column vectors or Dirac representation. So Dirac notation involves writing the numbers in a ket form, which describes the column vector, where ket 0 refers to the vector 1 and 0. The way these vectors encode the information is that the first value represents the coefficient of ket 0, and the second value represents the coefficient of ket 1. Hence, naturally, ket 1 will also be 0, 1 as a column vector. And any generic state, ket psi, will be alpha, which is alpha ket 0 plus beta ket 1 in Dirac notation, can be written as a vector as alpha beta, because this is the probability amplitude associated with ket 0, and this is the probability amplitude associated with ket 1. And we saw that many times that the X gate, represented by an X on the circuit, which has a matrix 0, 1, 1, 0, can be used to flip the probability amplitudes of alpha and beta in any vector state, ket psi. And we know that multiplying a matrix onto a column vector gives us another column vector. So it's a linear transformation, and it must be a unitary matrix. This is analogous to actually applying the X gate on the state, and the output state refers to the output of the X gate. So when we apply X to some state phi, which we said could be represented as alpha, beta, when we literally multiply this matrix X onto it, we obtain beta into ket 0 plus alpha into ket 1, which flips the probability amplitudes of 0 and 1. So let's have a look at the proof of this. If I consider some generic state as ket phi, which is alpha into ket 0 plus beta into ket 1. If I represent this as a matrix, as a vector, sorry, it'll be alpha into ket 0 and beta into ket 1. Now to apply the X gate onto this phi, it is as simple as multiplying the matrix for the X gate, which we saw was 0, 1, 1, 0. Multiplying this matrix onto alpha, beta, what do we get? So let's do the multiplication. So first is 0 into alpha plus 1 into beta gives us simply beta. And 1 into alpha plus 0 into beta gives us alpha. So hence we obtained, in Dirac notation, we can write as beta into ket 0 plus alpha into ket 1. So what the X gate basically did was it flipped the probability amplitudes from alpha beta to beta alpha into ket 0 and ket 1. So that's what the X gate does. Now let's look at the next gate, the Hadamard gate. It's used to create an equal superposition state of the 0 and 1 states when applied to 0 and 1. And this is its representation in a circuit with an H, and it has the matrix form 1 by root 2 into 1, 1, 1 minus 1. And we see that when we apply it on 0 and 1, we get equal superposition states of 0 and 1 with 1 by root 2, because when we square 1 by root 2, we get a 1 by 2 probability of measuring both 0 and 1. And the difference being applying Hadamard to 0 and 1, we get a plus and minus respectively. And this minus mathematically represents a 180-degree phase difference between the 0 and the 1. So let's actually apply this on 0 and 1 and see and prove if it's actually correct. So let me just clear the whiteboard and continue. So if we apply the Hadamard gate onto 0 state, we are simply multiplying this matrix 1 by root 2 into 1, 1, 1 minus 1 into this 0 state, which is 1, 0 as a column vector. So now if you do the multiplication, 1 into 1 plus 1 into 0 gives us 1, and 1 into 1 plus minus 1 into 0 gives us 1 again. Sorry, it gives us 0. I'm sorry, gives us 1. Yeah. And 1 by root 2 remains as it is. So what we've got is 1 by root 2 into ket 0 plus ket 1, which is an equal superposition state. Similarly, you can try if you multiplied Hadamard with 1, we simply multiply this by 0, 1, and we should be getting a minus state here, which represents a 180-degree phase shift. Let's visualize exactly how this looks on a block sphere. First, let's simply look at the X gate that we should have seen a little bit earlier. So when we apply the X gate on the ket 0 state, we flip the amplitude from 0 to 1. So if I click on this button here, we see that the amplitude got flipped by 1. And the reason it's called an X gate is we can see it's kind of a 180-degree rotation about this X axis. And you can actually see that if you apply X again on 1, its probability will get flipped back to 0, which we see over here. Yeah. Now, if we consider the Hadamard gate, we saw when we applied it on 0, 1, we got an equal superposition state of 0 and 1. That is, the state vector on the block sphere is right between 0 and 1. So if I apply the Hadamard gate, we see that's exactly what happens. The state 0 and 1, the resultant state has an equal probability of being measured as 0 and 1. And if we consider when we apply the Hadamard on the 1 state, if I apply the X gate to start in the 1 state, followed by a Hadamard, what happens is we also get an equal probability of 0 and 1 state. However, it's different from the earlier state, which was here, because it has a 180-degree rotation, also known as a phase. And the phase is important because even though 0 and 1 and both of these states had an equal probability of being measured as 0 and 1, when we apply the Hadamard gate on this state, we get 1. Whereas initially when we were applying the Hadamard gate on this state, we get back 0. So in a way, Hadamard is its own inverse, and the phase has an actual physical significance, even though the probabilities of being measured as 0 and 1 are the same. Now let's consider the next gate, which is the Z gate. It simply flips the phase. Like I discussed, like the phase is a 180-degree rotation about the Z-axis. So the matrix for it is 1, 0, 0, 1. And if I apply it to a state phi, which is alpha ket 0 plus beta ket 1, I get alpha ket 0 minus beta ket 1. Let's just very quickly see this over here. If I just clear the board and I apply the Z gate on phi, it's the same as multiplying the matrix 0, 1, minus 1, 0. I'm sorry, it was a 1, 0, 0 minus 1 on the state alpha beta. So if I multiply alpha into 1 plus 0 into beta is nothing but alpha, and 0 into alpha plus minus 1 into beta is minus beta. So we got alpha into ket 0, if I write this in Dirac notation, minus of beta into ket 1. So I flip the phase. And if you look at the visualization of this, if I started off with this equal superposition state between 0 and 1 and apply the Z gate, I get the same probability of measuring 0 and 1, but with a 180-degree phase shift. If I look from the top, I see it went from this state and rotated 180 degrees or pi radians. And this is represented mathematically just with a minus symbol instead of a plus. And why exactly is that the case? It's because whenever we rotate a vector along the real axis by some theta degrees, we can represent it as multiplying it by e power of I theta. And in this case, the value of theta is pi because we're rotating it by pi or 180 degrees. And hence, this is equal to minus 1. And that's why we chose a minus 1 to represent a 180-degree phase shift. Okay, so that was the Z gate. Now let's just look quickly at the C naught gate. So we saw what the X gate does. It flips the amplitudes. The C naught or the controlled NOT gate is simply applying the X or the NOT gate only if some condition or control qubit is equal to 1. So this is actually not a single qubit gate, but a 2-qubit gate, where the control qubit, if the control qubit is 1, then only an X gate or a NOT gate is applied to some target qubit. And it's represented like this in a circuit, where the solid dot is the control qubit and the X is kind of like the target qubit. And its matrix is a 4 cross 4 matrix since it doesn't apply on a single qubit but a two qubit system where the qubits can have four possible values 0, 0, 0, 1, 1, 0, or 1, 1. That's why it's a 4 cross 4 matrix. So if we just look at how C naught is applied, we look at C naught applied to 0, 0. 0 is the value of the first qubit and 0 is this value of the second qubit when we're applying the C naught. But we said when in the C naught gate, when the control qubit is 0, we do not apply any NOT gate on the second qubit. Hence, the output is 0, 0. Similarly, for this state, the first control qubit is 0. Hence, we do not apply any NOT gate on the second qubit, and the state remains as it is. Whereas if we consider these two cases, where the control qubit is 1, we must flip the value by using an X gate on the second qubit, whilst keeping the first qubit unchanged. So the value is 1 and 1 and 1 and 0 respectively. I will leave the proof of this as an exercise simply in the same manner that we did. Take this matrix and multiply it by the 0, 0 state, 0, 1, 1, 0, and 1, 1 state. Let's just take a very simple example of the 1, 0 state to show what I'm talking about. So when we apply this C naught gate on the state 0 1, 0, let's say, where the first qubit is the control qubit. So we have to multiply this 4 cross 4 matrix, which was 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. We multiplied by 1, 0. And this is represented by a four-dimensional column vector, not a two-dimensional one, because again, we're dealing with a two-qubit system here. So there are four possible amplitudes that we must consider in the superposition. In this case, there's no superposition. It's simply the state 1, 0. So the probability amplitude of 0, 0 will be 0. For 0, 1 will be 0. But the state 1, 0 will have the probability amplitude 1. And the state 1, 1 will have probability amplitude 0. Now, if we just do the multiplication, you can see in all of these terms, the first column will be equal to 1. Sorry, 0, because we're multiplying everything by 0 in a way. Second column also 0 times 0, 1 times 0, 0 times 1, 0 times 0, we get 0. Similarly, for this also 1 into 0 plus 1 to 0 is 0. But in the last column, we get 1 into 1 plus 0 into 0, which is 1. And the output state we're getting is ket 1, 1. So we saw that basically when 1 was the control bit, we applied the NOT gate onto the second qubit to get 1, 1 as the output. So you can also similarly try this for the other cases in your free time for practice. Now, entanglement refers to when two or more qubits have their measurement values correlated in some sense. So if you have a two qubit system, and if I consider this circuit, which is used to create entanglement, then if I measure one qubit, I can figure out the value of the other qubit because their measurements are correlated. And Bell states refer to a very specific type of entangled states, which refer to exactly two qubit systems, which are maximally entangled. Maximally entangled means once I know the measurement value of one qubit, with 100% certainty, I can determine the other value if I know the state. And this is the circuit for creating a Bell state. That is, you first apply a Hadamard on the first qubit, followed by a C0 gate with the first qubit as the control and the second qubit as the target bit. And if we kind of do the math here, we see the initial state, which is phi naught, will be ket 0, 0, because both the qubits are 0. After applying the Hadamard gate on the first qubit only, the second state of the circuit, which is phi 1, will be represented as 1 by root 2 into ket 0, 0 plus ket 1, 0. Why? Because the second qubit is 0 in both cases, because we didn't apply anything on that. But applying the Hadamard gate on the 0 state, we saw that it generated an equal superposition of 0 and 1, 1 by root 2 into 0 and 1. And we just added 0 because the second qubit is 0 in both cases. Following this, if you apply a C0 gate with the first qubit as control and the second qubit as the target, in this first term, we see that the first qubit is 0, so we don't need to apply any X gate here. Whereas in the second term, we see the first qubit is 1, so we flip the second qubit and we get 1, 1. And this is the output of the state. And this state is called a Bell state because as you can see, there's a 50% probability because 1 by root 2 whole square is 1 by 2 of measuring both the qubits in 0 or both the qubits in 1. There's a 0% probability of measuring 0, 1 and 1, 0. So in a sense, the measurement of both of these qubits are correlated such that they must have the same value upon measurement. That is why they're called entangled qubits. And we can also create 4 specific Bell states simply by applying the X gate before or not applying the X gate on either of the 2 qubits. So now let's go to the actual superdense coding part. So in normal English terms, we know that dense kind of means when we say something is dense, we means it can pack more stuff into smaller space in some sense. So when we're talking about superdense coding specifically, it means it's a method through which we can encode 2 classical bits of information in a dense form through a single qubit. So we're somehow representing 2 classical bits of information using a single qubit. And to do this, we utilize the phenomenon of Bell states and entanglements. So this is the actual circuit through which superdense coding is conducted. So initially there are 2 qubits with the state 0 and 0, and we create a Bell state. Use in this box, this is the same circuit that we used to create a superposition state called the Bell state by applying the Hadamard gate followed by a C0 gate. After this superposition Bell state is created, then one sender, which we might call Alice, can keep the first qubit, and the second qubit can be kept by a recipient called Bob. And now using these gates, Alice, who has 2 classical bits of information, say B1 and B2, can encode it into her part single qubit, encode 2 classical bits of information into a single qubit. And using these operations, Bob can decode the sent over single qubit using his part of the Bell state to obtain the original 2 classical bits of information just by sending a single qubit from Alice to Bob. So now let's exactly see how this happens by seeing what happens after each application. If we consider the first part, we've already kind of seen the proof. After applying Hadamard gate and the CNOT gate, we get an equal Bell state. So that is represented over here using 1 by root 2 into ket 0, 0 plus 1 by root 2 into ket 1, 1. I just took 1 by root 2 common. So this is our Bell state that outputs once we've created the Bell state. Then Alice and Bob may move apart, and Alice now wants to send 2 classical bits, B1 and B2. So what Alice does is, if the first classical bit has a value of 1, she will apply the Z gate onto her qubit. And if the second classical bit is 1, she's going to apply an X gate onto a qubit. Because it's like a C0 gate, right? But it's not C0 because it's controlled by a classical bit. Otherwise, she will not apply any of the gates. So there are basically 4 possible combinations of these bits that we might want to be able to transfer: 0, 0, 0, 1, 1, 0, and 1, 1. So accordingly, Alice may or may not apply these gates. Once her qubit has been encoded, once these 2 classical bits have been encoded into her qubit, then she can send her single qubit to Bob. And using that sent qubit and his part of the Bell state, first he applies a C0 gate with the first sent qubit as the control bit and the second, his part of this Bell state being the target qubit, followed by a Hadamard gate on the sent qubit, and simply measures both of the qubit after that. After which he's guaranteed to get the initial 2 bits, classical bits B1 and B2. So now let's consider the mathematical proof of how exactly this works. So the first case would be when B1 and B2 are 0. So let's consider the case when B1 and B2 are both 0. That is, what application does Alice do? Nothing, because both of them are 0, so she neither applies an X gate nor does she apply a Z gate. Following which she sends that qubit over to Bob. Now Bob applies the C0 with the first qubit as control and the second qubit as target. So now let's apply it. So the C0 gate we're going to apply onto this state, where the first qubit is the control and the second qubit is the target. So if you look in this term of the state, 0 means that we do not need to apply any operation to this term. However, when the first qubit is 1, we apply a NOT gate onto this state. And what do we get as the output? We get 1 by root 2 into ket 0, 0, because that term remains as it is, plus this term, it changes from 1, 1 to ket 1, 0. So after applying this, we can kind of see the entangled state is kind of destroyed now because entanglement meant that measurements were correlated between both the qubits. But in this case, now we see, regardless of the value of the first qubit being 0 or 1, the second qubit is always 0. And hence, we can kind of treat it as a separate entity from the first qubit. And we can factor it out from the equation since it's a common term. So we can write it as 1 by root 2 into ket 0 plus ket 1. However, we can factor out the ket 0 using a tensor product. So now we've separated out the second qubit, and always this second qubit will be measured by Bob as B2. And if we consider this first qubit now, what is the remaining part that Bob has to do? Needs to apply a Hadamard gate to the first qubit. So what happens when we apply a Hadamard gate to this state? 1 by root 2 into ket 0 plus ket 1. Let's see. So applying the Hadamard gate onto 1 by root 2 into ket 0 plus ket 1 is the same as applying, we have to say multiply the Hadamard matrix, which is 1 by root 2 into 1, 1, 1, minus 1. Into this state, how do we represent as a vector? Well, we can see it's basically 1 into root 0 and 1 into ket 1 and 1 by root 2 on the outside. So if we take 1 by root 2 out again, we get 1 by root 2 into 1 by root 2. Sorry about that. Yeah, 1 by root 2 into 1 by root 2 into this 1, 1 state. Let's actually do the multiplication now. So 1 by root 2 into 1 by root 2, simply 1 by 2 multiplied by 1 into 1 plus 1 into 1 gives us 2. And 1 into 1 plus minus 1 into 1 gives us 1 minus 1, which is 0. So what we get here is simply the state 1, 0, which is nothing but ket 0. So the first qubit now transformed from this equal superposition state through the Hadamard gate to ket 0. So it kind of undid the superposition state because Hadamard is its own inverse. After applying the Hadamard, we got an equal superposition state, and after applying it again, we got ket 0. And this is the first qubit that Bob measures to be the first bit, right? Because after this, he applies measures both the qubits. So is this correct? Yes, because we started off with the 0, 0 state, and we measured what? B2 as 0 and B1 as 1. So we got 0, 0 as the output as well. Hence, Alice has successfully sent a single qubit which encodes two classical bits of information, and Bob has decoded it. Now let's consider the second case of 0, 1 as the input, because the classical bits can be 0, 0, 1, 0, 1, 0, 0, 1, and 1, 1. Let's take the case of 0, 1 in this case. So what does Alice do to the superposition state when 0, 1 is the case? So the first bit is 0, so no need to apply the Z gate. The second qubit, second classical bit is 1, so we apply the X gate onto the qubit. So we started off with the Bell state, again 1 by root 2 into ket 0, 0 plus ket 1, 1. And she applies the X gate on the first qubit now because this classical bit has 1. So let's apply the X gate onto the first qubit. What happens? Simply just flip the value of the first qubit in both of the terms. We get 1 by root 2 into ket 0, ket 1, 0 plus ket 0, 1. After applying this, Alice needs to send a qubit to Bob. And now Bob applies these two operations, the C0 gate and the Hadamard gate. So now that we've done this routine, we can kind of speed it up a bit. Apply the C0 gate to this state. What happens is the first qubit here is 1. So we flip this qubit. But the first qubit is 0 in this case, so we don't need to flip this qubit. So the output of that will be 1 by root 2 into ket 1, 1 plus ket 0, 1. And again, in this case, now Bob kind of measures the second qubit. We can see that the superposition has been undone over here because there's no correlation. Regardless of the first qubit's value, second qubit is always 1. So we can also, again, factor this out of the term, and you get 1 by root 2 into ket 1 plus ket 0. And we factored out ket 1 as the second qubit. And we can kind of measure this as B2 always. And again, Bob applies the Hadamard gate on the first qubit. So this state is actually exactly the same state. If it's commutative, right? So This is the equal superposition state of 0 and 1. And applying Hadamard gate on this, we always get 0 itself, which we measure as B1. So what have we measured? B1 is 0 and B2 is 1. Have we not successfully decoded the 0, 1 message sent by Alice through a single qubit? I'll just consider the last case, the third case as the last one with the 0, 1, and I'll leave the last one to you as an exercise. So if I consider the case 1, 0, the first qubit, the first classical bit is 0 in this case, not the second one. That means I must apply a Z gate on the first qubit, but not the X gate. So we started again with the Bell state, 1 by root 2 into ket 0, 0 plus ket 1, 1. And we apply the Z gate now. What happens in the Z gate? I said that the phase gets flipped from a plus to a minus. So the output of applying the Z gate will give us this state. 1 by root 2 into ket 0, 0 minus of ket 1, 1. So now after applying this, Alice sends a qubit to Bob and he applies the exact same thing. So I'm going to do this quickly again. Applying the C0 gate with the first as control. In this case, 0, so no need to flip. In this case, 1 is the value of the first qubit, so we flip this using an X gate. And the output we get is 1 by root 2 into ket 0, 0 minus of ket 1 into 0 in this case, because we flipped the second qubit. And again, it undid the superposition, so we can kind of see the value of the second qubit is 0, regardless of what the first qubit is. So we can see that the second bit B2 is going to be 0 always. Now, if we write it like the first qubit is going to be 0 minus of 0, minus of ket 1 now. What happens next is here, Bob must apply a Hadamard gate onto the state. And as we saw, Hadamard gate, when it was applied to 0 plus 1 state, it was giving us back 0. But when it was applied to 0 minus 1 state, it was giving us ket 1 as the output. And you can verify this on your own by using the exact same method we did by multiplying the matrices. But we know that we get ket 1 as the output always. And once this is measured by Bob, we say B1 is always 1. So now if you consider these two cases, again, we got 1, 0 as the output, which is the exact same input that we were supposed to have. And it was transmitted to a single qubit, hence super dense encoding of the information. Now you can kind of do the encoding for 1, 1. You can, I'm not going to do this here. I'm going to leave it as an exercise for you to do extra at home. It's basically quite simple because it's combining both the cases of 1, 0 and 0, 1, whereby we are applying both the X gate and the Z gate to the qubit before transmitting it to Bob. And as expected, we should get 1, 1, and you can prove this on your own using the exact same method we have shown here. And just to like even visually just kind of understand, when we were looking at the Hadamard gate, if we applied it once, we got the equal superposition state. And if we applied it again, we got back 0. Oh, sorry, Hadamard. If we applied it back, we got back 0. And whereas if we started with 1 and we applied the Hadamard, we got this again, the state which is 180-degree phase flip. And if we applied it again, we get back 1. Like this state was 1 by root 2 into ket 0 plus ket 1, whereas this state was the phase flip one with ket 0 minus ket 1, which we also proved mathematically, that we get back the same state after multiplying the matrix. So now that we understand how exactly the circuit works for superdense coding, with proof of how for each of the cases 0, 0, 0, 1, 1, 0, and 1, 1 I left as an exercise, how we can encode it into a single qubit and transmit it by applying these gates. And for those of you who are in the quantum teleportation workshop, you might seem this as quite familiar. The only difference being that the input for the sender is not a quantum state, it is two classical bits, and that these operations were kind of applied at the sender side, and these operations were applied on the measured qubits on the receiver side for the quantum teleportation. In a way, it's kind of an opposite of quantum teleportation, superdense coding. So we've seen the proof. Now let's look at the Qiskit implementation of the circuit, which is almost trivial once we've seen the circuit. So let's kind of hop onto a Jupyter notebook and see how it's implemented. If I create a new notebook, okay. So the first step is to create an actual circuit. So what are the steps involved in creating a circuit? What components does our circuit have? I'm not going to consider this as part of our circuit. I'm just going to consider it as an input given to the circuit. But a quantum circuit involves mainly these two qubits in a quantum register, as well as the two classical bits that are measured by Bob in a classical register. So let's first create that. So I first need to import some dependencies from Qiskit. So from Qiskit, I want to import the quantum register, which we're going to use for our qubits. I'm also going to import the classical register, which we are going to use for our classical bits, and an object called, or a class called a quantum circuit, which is going to consist of these quantum register and classical register. So first, I'm going to create a quantum register called Q, which is a quantum register of 2 qubits. And I'm going to give it a name, so let's say QReg. And C is our classical register, consisting of 2 classical bits, and I'm going to call it QReg. Sorry, CReg, sorry. Then I can create a quantum circuit called QC using this quantum circuit class by Qiskit, consisting of the quantum and classical register. There's also an inbuilt function of quantum circuits called draw, which kind of displays the circuit that the kernel initialized. Yeah. So you can see there's a classical register with 2 qubits. So a quantum register with 2 qubits and a classical register with 2 bits. And to make it look better, we can put it in an output format called matplotlib. And if we kind of look at it, we see over here, there's 2 quantum bits in the quantum register, and there's 2 classical bits in the classical register. And I just put reverse bit switch 2 because the way I've chosen to denote it is Q1 is the top qubit and Q0 is the bottom qubit. So here, Q1 is the top qubit and Q0 is the bottom qubit. So initially, by default, all circuits in qubits start off with 0, 0. So what is the first step we need to do? We need to create the bell state between Alice and Bob, which involves the Hadamard and the C0 gates. So let's do that. Let's first create a bell state. So the bell state first involves what? Putting a Hadamard on Q1. So onto the quantum circuit, we apply a Hadamard gate represented by the H primitive, and we apply it on which qubit? Q1, which is kind of indexing the quantum register. So Q1. After this, what do? We need to apply a C0 gate with this is the control and this is the target. So we apply a C0 gate represented by CX because the NOT gate is nothing but an X gate. With what? What is the control bit? It's Q1 and target bit is Q0. If we kind of plot it, we see this is exactly what we have. Hadamard on the first and a C0 gate. And so now we've created the bell state successfully. And just for aesthetic purposes, I'm going to add a barrier. So as you can see, a barrier just adds a dotted line. So we've created the first part of the circuit. Now, based on the input bits, which is some two-bit string, we want to apply at Alice's end to encode the super dense qubit. With the first bit, we might apply the Z gate based on if it's 0 or 1. And with the second bit, we may apply the X gate if it's 0 or 1. So the way I'm going to implement this is I'm going to say encode the input. Let's say that a classical input is passed to us as a two-bit string. Let's say 0, 0 or 0, 1 or whatever, 1, 0 or 1, 1. So what we need to do, if the first bit is 0, we want to apply a Z gate on the first qubit. So if the classical input's first bit is equal to 1, I'm going to apply onto the quantum circuit a Z gate. On which qubit? Q1, because it's the top qubit. And similarly, if the classical input's second bit value is 1, I'm going to apply an X gate onto the quantum circuit. And if I kind of draw it, 0, 1 was the input, right? So the first bit was 0, so no need to apply Z, but the second qubit was 1, so I apply an X gate. If I passed it as 0, 0, I would apply C no gates. If I passed it as 0, 1, I apply the X we saw. If I pass 0, 1, 0, then we apply only the Z gate. And if I pass 1, 1 as the input, then we get both Z and X gate being applied. So now Alice's encoding using the classical bits has finished. So let's just add a barrier to make it look better. What's the next step? Alice kind of sends the qubit. Here we don't have to like physically send it because like we're simulating it on like a single circuit. So let's just leave that part. And now look at what Bob is doing to decode the classical message. So first is applying a C naught gate with Q1 as the control and Q0 as the target. So, and followed by that, he applies a Hadamard on the Q1. So let's kind of do that first. So decoding by Bob. So what does he do? First, he applies a control NOT gate with Q1 as the control and Q0 as the target, followed by applying a Hadamard gate on Q1. Sorry, yeah. After this, he has to obviously measure it, right? Because these are qubits at the end of the day. To get classical values, he needs to measure both of the values from the quantum register onto a 2-bit classical register that we have created. So let's quantum circuit dot measure the quantum register called Q onto the classical register called C. Now let's kind of see how the circuit looks. So it works, right? We apply the C naught gate followed by the Hadamard gate on 0 and 1. And this is exactly the completed circuit for superdense coding. But now let's actually run the circuit by using a simulator and see if it actually works. So in this case, the input was 1, 1. Let's see if when we measure these two qubits at the end at Bob's end, if we actually get 1, 1. So there's a package called Qiskit Air, which includes an object called an air simulator, which we use to simulate quantum circuits. So first we need to pass a job. A job is basically like a task or a process that you pass to this simulator of the quantum computer that runs the quantum circuit. So job we first need to create an air simulator by using this air simulator constructor. Now we've created an air simulator and we want to run our quantum circuit. So we do it by calling the run function on our quantum circuit called QC. And there's an additional parameter called shots. So shots refers to how many times you want to run the circuit. In this case, even one time would suffice, but just to justify that every time we're going to get 1, 1, I'm just going to run it 100 times. It's an arbitrary choice. So now once I've run this, I need to just get the actual data out. So I'm going to store it as a counts, as a dictionary, where I'm going to get the result of the job, and I'm going to get the counts. That is how many, the counts refer to how many times different values are measured. So I'm going to get the counts after running the quantum circuit, and let's print out these counts. So as you can see, after simulating this, we get 1, 1 as the output. So 1, 1 was actually the input as well, and 1, 1 is the output. All of the 100 times we got 1, 1. So that means we have successfully encoded two classical bits into a single quantum bit. If I did 0, 1 as the output, as the input, sorry, we only applied the X gate because 1 was the second qubit, and we got 0, 1 also when Bob had measured it. So it worked. If we do 1, 0, then we only apply a Z gate since the first qubit is 1. And then Bob also, after running this, gets 1, 0 every time. Lastly, if we consider the last and final case of 1, 1, we apply both an X and Z gate since both the classical bits are 1. Followed by, if we simulate it, we get 1, 1. And we can also visualize it using a histogram. In this case, it really doesn't make sense since like only one value is being measured, but I will just show you. So from the Qiskit has a visualization package from within which there's a function called plot histogram. And if we pass a dictionary of counts uh, into this plot histogram function, then we can just kind of get like a bar chart with like the different measurement outcomes. Anyway, in this case, it doesn't make sense. It's all of the 100 times we are getting 1, 1 as the measurement. So this is like a Qiskit implementation of our superdense coding where all the 0, 0, 0, 1, 1, 0, and 1, 1 works. So yeah, that is the conclusion of my talk, and I would like, if there are any questions, I'd be open to answering them. Are there any questions?
No questions from my end.
None from my side.
It was nice, Archit. Sorry, I fall asleep.